We live in a world defined by invisible signals, but it wasn't long ago that our technology had to be physically tethered to a wall. If you've ever looked at a circuit board, you know electricity likes a closed loop. That makes an antenna look like a mistake, a single wire that just ends, pointing into nothing. It helps to think of that wire as an electron shaking device. To see how it works, we must look beneath the metallic surface, visualizing the subatomic forces that turn simple metal into a launcher for energy. Imagine a pool of water. If you place your hand in and keep it perfectly still, the water stays calm. A stationary electron acts the same way. It has an electric field, but it doesn't create a wave. If you move your hand steadily across the pool, you'll create a wake, but still no propagating waves. This is like direct current, where electrons flow steadily in one direction. You get a magnetic field, but nothing radiates away. But if you shake your hand back and forth aggressively, you'll see ripples start to travel across the surface. This is the logic behind alternating current. We use it to drive electrons into an antenna, so they are forced to rapidly accelerate and decelerate over and over again. This diagram captures the difference. On the far right, that constant shaking is what triggers a self-sustaining ripple in the electromagnetic field. This was the breakthrough James Clerk Maxwell described in his equations. Only accelerating charges have the power to launch waves into space. We can see this in action using the simplest antenna model there is, the short dipole. It's just a straight piece of wire carrying that alternating current. Right next to the wire, the near field, energy just sloshes back and forth like a spring stored nearby. But as we move further away, the frequency pushes the energy until it eventually detaches from the sloshing near field. Once it hits this far field, the wave is entirely independent. It's a self-sustaining ripple that no longer needs the antenna to keep moving. This pinch-off is the moment the cord is truly cut. If the fields didn't separate like this, all that energy would just fall back into the wire, and wireless communication would be impossible. It's common to imagine an antenna acting like a light bulb, glowing in a perfect sphere. In reality, the signal has a very specific shape. This is the radiation pattern for a dipole. Instead of a sphere, energy expands as a massive 3D donut. Because of this shape, there are dead zones at the top and bottom. Stand directly above the antenna and you wouldn't receive a signal. This directional math is a constant for every dipole antenna ever built. It's why engineers are so careful about how they point their equipment. To get the strongest signal, you have to aim the meat of the donut at your receiver and avoid those vertical nulls. From the perspective of the circuit driving the antenna, something strange is happening. It's constantly losing energy into the void, but there's no clear place on the wire where that energy is being spent. Since that energy is physically leaving the system and never coming back, the transmitter experiences the air itself as a source of drag. To the circuit, this drag feels exactly like a phantom component draining power. This is why engineers treat the antenna like a resistor, specifically a phenomenon called radiation resistance. This only works efficiently if your antenna length matches the broadcast wavelength. Imagine sending a 1 MHz AM radio signal, which is 300 meters long, through a tiny 1 meter wire. The physical mismatch makes radiation resistance drop to almost nothing. With the resistance that low, the energy can't escape as a wave. Instead, it reflects backward, which can overheat and eventually destroy the transmitter. So, the next time you use your phone, remember, you're shaking electrons to launch waves. Those waves travel in the shape of a giant donut, and that energy loss is the only thing the transmitter feels as it sends your data into the world.